today's second session, Dr. Manjunath M. Sir, I welcome you, sir, for the today's session.
Thank you.
The participants, the second session is about to start. I request all of you join. And Professor Manjunath is my senior research fellow colleague and also my the faculty colleague at BIT Davanagere earlier, and he was my senior research colleague at IIT Madras. On behalf of organizing committee, on behalf of institute, and personally, I welcome Professor Manjunath for the today's FDP program, sir. Welcome you, sir.
Thank you. Thank you.
Now I request my colleague, Professor S.A. Pushpalata Madam, to introduce Dr. Manjunath M. to all the participants of this faculty development program. Over to Madam.
Thank you, sir. Good morning, everybody. It gives me an immense pleasure to introduce an academician and a researcher to this session, Dr. Manjunath Mahadevappa. Dr. Manjunath Mahadevappa presently sir is working at IIT Kharagpur as a professor. Sir has received the BE and MTech degrees from University of Mysore in 1990 and 94 and PhD degree in biomedical engineering from Indian Institute of Technology Madras in 2001. He joined Downey Eye Institute at University of Southern California, Los Angeles, California, USA in 2001 as postdoctoral research fellow. During 2004-2005, he worked as postdoctoral scholar at Department of Biomedical Engineering, University of Kentucky, Lexington, USA. He is currently working as professor at Indian Institute of Technology, Kharagpur, India. Dr. Manjunath is a senior member of the IEEE EMBS Fellow of the Institution of Engineers, India, a life member of Biomedical Engineering Society of India. He has published over 50 peer-reviewed research papers, books, and book chapters on medical imaging and advances in therapeutic engineering. He served as the conference co-chair of the IEEE International Conference on Point-of-Care Healthcare Technologies in 2013. His research interests include biomedical signal and image processing, bioinstrumentation and biosensors, retinal and neural processes, electrical retinal stimulation, rehabilitation engineering, and biorobotics. He is currently serving as associate editor of the IEEE Journal of Translational Engineering in Health and Medicine. So on behalf of our institute, I once again welcome you, sir. Okay, sir, you can start the session.
Thank you. So thank you, Dr. Mallikarjun and the university team to in organizing this program. And today I would like to share some of the work that has been carried out in our laboratory by making use of this artificial intelligence method. So over this presentation, I would talk more about the different hemodynamic parameters, cardiovascular hemodynamic parameters, and how we are able to correlate these clinical parameters with the help of a device called impedance cardiography or impedance plethysmography. So I would use alternatively impedance cardiography and the plethysmography as the application here is mainly to analyze the cardiovascular events. So in this talk, I would this is how I organize my presentation. I would give brief introduction about introduction and also the prior art about this method, the impedance cardiographic method. Then the research objectives and the impedance plethysmographic technique. Then development of the electrode skin contact impedance model. Uh, Followed after studying the model, we proposed development of the device, impedance cartographic device. Uh, uh, then we have two experiments that we conducted. One is on correlating the impedance cartographic signals with the uh, conventional uh, the blood pressure measurement that is done in the clinical setup, uh, followed by other hemodynamic parameters. And in the second experiment, we try to correlate this the, the signal that we are obtained from this impedance cartography to localize the arterial vascular stenosis in the coronary region, and try to detect and if possible even to localize that where exactly the stenosis is taking place. And of course, for that work, we have we did a collaboration with the Department of Cardiology in Kolkata Medical College, where we were able to record these signals from the interventional subjects when they were undergoing the procedures. So, with this, uh, let me take to the introduction. So, as you know, that nearly 17 million deaths worldwide, occurring. This statistics is up to the 2015. Maybe it is still, that this number may be much more. And it is also expected that 23 million deaths by 2030 due to this cardiovascular disease. And the need is that we need to have an early clinical analysis and detection of these events. So for that, the main cardiovascular parameters or the hemodynamic parameters are the pressure pulses, the venous pressure, and the cardiac output. Currently, the methods that are available to measure and also to evaluate the clinically the hemodynamic parameters, it's quite expensive, and it requires also the expert supervision of the pulmonologist or the expert physicians. So by making use of this impedance cardiography instrument, so we may come up with a non-invasive technique where we could predict the healthy state of the hemodynamic parameters of a subject. So hence we are proposing this impedance cardiography as an alternate solution. In this particular device, way back in 1940s, people started exploring the use of bioimpedance measurement. So at that time, these bioimpedance measurements were used to estimate the fat-free mass of the human body. So later on, it has come up to the different applications, and people started working on exploring this bioimpedance technique. And as later as
Hello, sir. Sir.
this
Hello,
impedance
sir.
cardiography, yeah, can you hear me?
Yes, sir. Now, few seconds back, we have lost your audio, sir. Now it's coming, sir.
Now it has come.
Yes, yes.
Have we lost?
For
Now
few
it's okay.
seconds. Yeah, now it's okay, sir.
Okay. Yeah, please let me know whenever there is any break.
Okay, sir. Okay. Okay, sir. Okay. Thank you, sir.
Yes. So in as early as in early 2000, people started exploring this use of impedance plethysmography to relate central pressure. And in in the in 2007 and 8, a group studied how to use this impedance cardiography with chronic heart patients or heart failure subjects. And there was a study in 2009 where they tried to correlate the impedance cardiography with the invasive hemodynamic measurements in some of the advanced heart patients. So these sort of studies gave us a motivation that why we should not explore that, because India is again I mean having good number of cardiovascular subjects. So with this advancement of using impedance plethysmography technique in cardiovascular measurements, we try to bring in here in this presentation how we could use this impedance cardiography as against the cardiovascular uh, parameters like the blood pressure, the systolic pressure, diastolic pressure, and the other cardiovascular hemodynamics. So with this, prior art, as late as 2018, you could see that many groups, started exploring these correlative studies with ICG with the cardiovascular parameters at different, states. And there is one group they even try to develop this system based measurement for point of care applications. So with these prior arts in mind, we try to address here detecting the coronary arterial stenosis using this bioimpedance measurement, and it could be one of the viable solution for early clinical detection and analysis. And the another advantage here is that we'll have a reduced cost in terms of clinical diagnosis. So one need not go for expensive measurements. And this also could be used for mass screening applications wherever we need to do the cardiovascular screening. So with that, the research objectives in this studies are the development of the generalized electrode skin contact impedance model. So we try to understand the how electrode skin interface takes place, and what is its interface in terms of the impedance, electrical impedance. Then we designed the electrical impedance cardiography, uh, which is based on the aortic the pulse waveforms, um, and then we have two experiments that we have done. That is, we try to bring in the correlation or estimation between the blood pressure and other hemodynamic parameters uh, based on the proposed device. In the last study, we also bring in a correlation with the localization of the arterial lesions inside in the coronary region. So that is coronary arterial lesions, where we have taken these interventional data from the clinic, and from the same subjects we have also measured the impedance cardiography signals to correlate. So what is when we talk about bioimpedance, what is this bioimpedance and why it is so important? So before that, we need to know what are the electrical properties and how these biological tissue behaves when it is interacting with the electrical source. So one, this electrical property is mainly based on two different responses. One is the active response, the other one is a passive response. So when we take this human tissue, so we consider this tissue as a conducting medium or a conductor, and then this tissue is considered to be a heterogeneous property in nature, and uh, it has a finite volume conductor and behaves like a sourceless medium. And the tissue impedance can be represented by this single time constant three element model. That is, we have a series resistance with a parallel RC. This combination gives us a tissue, a model, electrical equivalent model of the tissue, uh, which behaves like a conductor. Then impedance plethysmography is basically involves the principle that the electrical impedance between two electrodes that are placed on the calf muscle. For example, if I am placing it on the lower half of the leg, lower part of the leg. So in the calf muscles, when we keep the two electrodes, uh, and when the electrodes are supplied with the potential, then the signal that we are observing is inversely proportional to the volume of blood that is present in the calf muscle in that area. So uh, here impedance plethysmography is when I say we are applying a electric potential across the muscle, means it is a non-invasive technique. We are not placing any electrodes internally into the body. So these electrodes are placed on the surface of the skin, and is a non-invasive technique for monitoring the stroke volume of the subject and other cardiovascular indices based on sensing the changes in the electrical impedance of the thorax. So in this impedance cardiography, what we do is we place two electrodes on the thorax or the chest wall of the human body, and then when we apply this electrical energy, that is electrical potential, this applying potential will cause a variation in in the impedance. So the change in the impedance across the electrodes is observed, and why these changes are observed? Because of the variation in the blood volume during each cardiac cycle. So you know that the heart is pumping blood to different parts of the body. So during each cardiac cycle, the blood is moving from the heart to the outside the heart to different organs. So this during this motion, so there will be a change in the electrical impedance, and we are interested in measuring that electrical impedance change this during this cardiac cycle. This the impedance plethysmography is of resistive in nature, in nature for the blood and muscle, for both blood and muscle at high frequencies, and it also has dielectric nature even at much higher frequencies. So we try to operate at some frequency range anywhere from 1 kilohertz to 100 kilohertz. So the two possible approaches for measuring the impedance here are applying a known voltage and measure the current. The other method is applying a known current and measure the voltage across. So the current that been applied for measurement here is in the range of 40 microampere up to a maximum of 10 milliampere peak to peak. So this is the current range. It is well below the safe limit proposed by the electrical stimulus coming. So up to 10 milliampere current would be safe to inject for this measurement. So in this measurement, there are two configurations. One is bipolar configuration, where you use only two electrodes, A1 and A2. So you measure the current across or the voltage developed across the two locations in the body, and then you estimate the bioimpedance. Similarly, in the tetrapolar arrangements, we have four electrodes. So A1 and A2 are the excitation electrodes where we apply alternating current. So this alternating current amplitude ranges anywhere from 40 microampere to 10 milliampere with a frequency range of 1 kilohertz to 10. Then, after applying the energy, we uh, we uh, uh, we are placing another pair of electrodes known as receiving electrodes R1 and R2. So we measure the impedance across these. So what happens? See, this is the skin underneath this electrode. This is the skin. So when the current is flowing through the skin underneath the skin, so there would be a variation in the impedance, mainly due to the many reasons. One is the flow of blood within the muscular region. So with that, there would be a change in the impedance, and we are interested in measuring that change. So in this study, we uh, uh, we need to this is a clinical study, and we have to include the we have to use this inclusion exclusion criteria. So why we do that? Because we have to select a group of patients who are eligible to study in this as a control and the intervention. So here, when we are including these groups for the study, uh, the participating subjects, this control group could be the normal subjects having no cardiovascular history or the ailments. So they are basically healthy subjects with normal electrocardiogram ECG. And in the interventional group, generally these patients will have an abnormal electrocardiogram ECG and stenosis of varying degree, like stenosis in the sense the blockage of the arterial vessels in the coronary region or the coronary artery block. So these are the groups that belongs to the intervention, and this is the control group. So we here in this study we are trying to control, we are trying to compare the results of these hemodynamic parameter from the normal healthy group to the interventional group, which is abnormal in nature in terms of their all the physiological parameters. And when we select these again interventional groups, we have to make sure certain exclusion criteria. So this is our inclusion criteria, that patient should have an abnormal ECG and should have this stenosis of varying degree of stenosis. While selecting these interventional group, we have to have certain conditions to exclude them. So one is that if any patient has an electronic implant, so you know that in this study we are applying a small electric current, and this current is of 40 microampere to 10 milliampere, and at a frequency of say 1 kilohertz. So when we are applying this stimulus for recording the impedance cardiography, the patient should not have any electronic implant. You know, some of the other cardiovascular patients are having this electronic pacemakers. So this, if anybody has electronic pacemaker, then obviously we should exclude that patient. And a patient with severe hypertension who has hypertension at the stage 2 and above will be eliminated, uh, and age below 18 years, then who has any septic shocks, if the patient has a aortic valve regurgitation. So this is one of the cardiovascular ailment related to the valves in the in the heart. So those patients are eliminated. Another group where a patient has a tachycardia is the condition where uh, the person has a heart rate of higher heart rate above 100 beats per minute, and a patient with underweight. So all these groups are excluded here. And this study, we have proposed this study to the clinical ethical committee of the institute at IIT Kharagpur, as well as the ethical committee in the medical college and hospital. So both ethical committee approved this study, and then only we carried out this work. Coming to the development of this skin electrode interface models. So here, while developing this, it is important to see the bioimpedance analysis, uh, the contact impedance. What should be the skin and electrode contact impedance? And this contact impedance acts as a barrier to record the accurate physiological signals, and it is an ideal modeling for impedance around the electrode skin interface, and it is very crucial. And also, as I told you, human safety is very important because we are applying a short electric current. uh, at the same time, we should look at the safety of the patient who is participating. This is a basic skin model, skin electrode model. So if you consider, this is my electrode that I am placing on the surface of the skin. So this is my skin, and under the skin we have epidermis and the dermis. There are different layers of the skin. And above the skin, we are placing the gel. Uh, it is an interface between the electrode material and the skin. So it brings down the contact resistance so that we are able to inject the current effectively. So this is the corresponding electrical equivalent of the electrode and the skin interface. So this, we have a voltage here that we are applying. Corresponding after that, we have this electrode equivalent circuit. So this is the skin electrode interface model. In this proposed modeling study, what we have done is we used finite element modeling using this COMSOL multiphysics software. So this is a finite element tool to understand how electrode tissue behaves when we apply certain voltage to the electrodes. We have considered in this model 6 centimeter by 4 centimeter patch of the skin with two copper electrodes of radius 0.4 centimeter, and we mark it as E1 and E2, and the skin depth perpendicular to the surface taken as 5 millimeter. For skin, the density is around 0.343 Siemens per meter, and with the relative permittivity. And for copper, it is 58 Siemens per meter, and epsilon or relative permittivity of 6. So as I told you earlier, excitation pulse with a sine wave of frequency 15 kilohertz, time duration of 66, microseconds, 66 microseconds. Then initially we applied current of 3 milliampere with 50% duty cycle. So this is the proposed model when we are applying the electric field on the surface of the skin through these electrodes. And the assumption in this model is that external magnetic field is negligible and there is no displacement current. The surface of the conducting or excitation electrodes are an equipotential surface. So we are assuming that that is when we apply certain potential, say 3 milliampere current we are applying. So we feel that it is applied equally across the all the directions of the electrode that is having interface with the skin. Then electric field intensity at the surface is directed towards the normal of the surface. So we are going perpendicular to the skin. So this is the model geometry. I have a width of 4 centimeter and the length of 6 centimeter. These are the two electrodes E1 and E2 where we apply the potential. So if you imagine the wrist, your arm, so we can place the similar width of 4 centimeter by 6 centimeter and place two electrodes on your the radial part of the hand. You know, in the hand we have this radial artery that is supplying blood to the fingers and the complete hand. So we are interested in applying on the radial artery of the hand, and then we stimulate. And these are the boundary conditions that were assumed here. That skin and electrodes with current conservation conditions, and when we take the edges of the skin. So edges means when the electrode comes in contact with the skin. So there are the edges of the electrodes. So these edges of the electrodes with the skin uh, with typically the electrical insulation is provided with zero energy. So that means we have a proper insulation. And electrode boundary, we have we measure the contact impedance uh, surrounding the electrode. The parameters studied in this model is current density, resistive loss, and electric field. So these are the three parameters. So this is a typical current density that we observed when after applying the current to both the electrodes E1 and E2 electrode. And this is the current density distribution after simulating a single excitation pulse with only one excitation pulse, and this is the response we observed for continuous excitation pulse. And we also measured the resistive loss in terms of watt per meter cube across the interface. So we can see the resistive loss is is also important because we are interested in measuring the impedance. You can see this is the electric field displacement. So here this is the location of E1 and E2 electrodes. You can see the electric field displacement that is measured in coulomb coulomb per meter square. This is the field distribution, and this is the total width of 4 centimeter and length of 6 centimeter. So two electrodes E1 and E2 are being supplied with the voltage, and what we do in between these two electrodes, we have kept R1 and R2 are the receiving electrodes, and we are measuring the impedance from these two electrodes. So these electrodes are supplying the electric field to this. So now these electric field will be will change depending on the flow of blood underneath the electrodes. So these electrodes are placed just above the radial artery in the hand. So for every cardiac cycle, there is a the peak and the trough corresponds. It is the arterial flow is basically pulsatile in nature with systolic and diastolic, you know, peaks. So accordingly, the impedance across these two electrodes, R1 and R2, will vary based on the flow of blood on these radial arteries. So we are interested in measuring that impedance. So from this model, we found that maximum electrode impedance was 4 kilo ohms with current density of 8 milliampere per meter square, and maximum current density is much lower than 10 milliampere per meter square. So this 10 milliampere per meter square is the maximum safety level that is proposed by you know the frequency dependent limits for electric and magnetic fields. Okay, so this is proposed by the uh, uh, group where one has to take care when we are applying the potential electric current to the interface. So in this case, we are applying only 8 milliampere per meter square. And the specifications of the excitation pulse is safe for the human subjects. So as long as we apply within 10 milliampere, we are operating in a safe mode. Now coming to the development of the device, here we proposed a tetrapolar based configuration with a safe limit, and specifications of the pulses are 15 kilohertz frequency, current with a 3 milliampere, and the source is of sine wave. If you take a look at the circuit implementation, so all of you, can you see this screen?
Yes, sir.
Yeah. Okay. Okay. So are you okay? So this is the circuit implementation uh, uh, of the impedance cardiography. So first we have a power supply, then the function generator, then we have a sine wave generation followed by op-amp subtractor, inverting amplifier, and after this we convert this voltage into a current. So this current will be given to C1 and C2. So in the previous model, so this is my C1 and C2 are the two electrodes, and these are the two recording electrodes or the receiving electrodes. So through these electrodes, we are supplying the electric pulse. So this C1 positive and negative, these two pulse will go here to the patients. And once it is given, so we have the other two electrodes, that R1 and R2. We receive that, from there we connect it to an instrumentation amplifier, then rectification now, and after modulation. So we apply this second order Butterworth filter, and this signal we call it as a Z, or the impedance value. So this is our impedance measuring output. So from here we what we do, we first differentiate and call it as dz by dt. Again we detect the threshold, and then we process this signal by measuring the detection of change in the peak by measuring its envelope. Then we get this the signal dz by dt. This is my impedance signal. So the processing of that bioimpedance Z is parallelly taken from this filter also and given to the microcontroller. So what happens now? I have this. I need to analyze the signal of the extracted features. So what I do is I take this signal, extract the features like uh, what are the different features from the impedance uh, signal. So then I also feed this to the trained neural network and, and also see the point of occurrence of the stenosis, and finally we display. So this is the overall structure of the circuit implementation. So we will go in the next block. You can see here. This is the processing of the filtered impedance cardiographic signal. So once we collect the input signal, we pass it through the A to D sampling hold and given to the memory. And then we read the signal here. Afterwards, what we do, we feed it to a microcontroller, and microcontroller will convert this signal back to analog in nature, from digital to analog, and we use a smoothing of the signal, and finally we get the envelope. So after getting the envelope here, we set a threshold and detect the peaks for identifying the uh, systolic uh, pressure peak, diastolic peak points. So these are very important, and also there is one peak called dicrotic notch. So that also we try to extract, and afterwards we feed it through the memory, and we read maximum points, peak point and the minimum peak point, and then we do the comparison using a comparator, and finally feed it to you know the calculations of systolic and the diastolic. So I'll show here one scheme here. So this is the actual raw impedance cardiographic signal. So we can see the after filtering this, we would be able to see that we have a peak systolic point, and then this is the peak diastolic point, and this is the baseline base point. So this is my one full cardiac cycle, and this is my second cardiac cycle. So in one cycle, we are interested in the peak systolic point here. So this is the peak systolic point, and this is the peak diastolic point, and this is the dichrotic notch here. This is the dichrotic notch. So now this is the signal, and afterwards, when you do the differentiation of this signal, we can see the first peak as is known as is noted as peak B, and the second peak is known as A. So we use this notation A and B corresponds to the first peak and the second for for estimating the diagnostic features from these signals. So let's go back to this differentiated impedance cardiographic signal, that is dz by dt. So what we do when we collect this input signal, so when I say input signal, so this is my filter DCP ICD signal. We will send it through Butterworth filter, then detection of highest crest, and we call it as a the B parameter, B peak, and then we take the input signal once again and feed it to second order differentiator and detect the highest crest here, and we call it as A. So using op-amp subtractor, we get A minus B here, and then we take A once again here, and we feed it to an op-amp based divider. So output of this divider we will get is A minus B divided by A. So this is my signal that we feed it to the divider, and the A to D converter to uh, memory we are sending it to the microcontroller. So what it does now, the microcontroller will display the calculation of this augmentation index. So this is my augmentation index given by A minus B divided by A. So by calculating this augmentation index, we can, we will be able to credit how healthy the subject is. So this is the main computational component here in order to correlate the impedance cardiography signal to the other hemodynamic parameters. Yeah, so these are the raw signal, then filtered impedance cardiographic signal, and then the differentiated signal. So what features are we extracting here? We are extracting the augmentation index. The augmentation index. So the augmentation index is defined by this uh, uh, A minus B divided by A. So that A corresponds to this. So this A is the second peak in the differentiated signal, and B is the first peak in the differentiated signal. So we detect this augmentation index, then systolic time, systolic area, diastolic area, area ratio, and time ratio. Also, we find the difference in amplitude of peak one and peak two. That is the first peak and the second peak. Okay, in one cardiac cycle. And then we also measure the third peak and the fourth peak of the second cardiac cycle. So we take two cardiac cycle information and then compute the difference in the amplitude of peak 1 and peak 2. So now in the first experiment, we did this blood pressure estimation with hemodynamic parameter. So the baseline characteristics in this study is that we use total number of subjects participated here, or 74 patients in the interventional group. That means these are all patients with cardiovascular abnormalities. Then these are the control group, around 30 patients, 30 normal groups. Again, we have a mixture of male and female accordingly. That 62 stands for the male and 12 female, yeah, and 19 male and 11 female. In this, the age group, again, mean age is 51 plus or minus 7. Here it is 28. So obviously you can predict. See, these normal groups are not actually recorded from the hospital. These interventional groups are from hospital, and this control group are from the IIT campus. They are all basically research scholars, and we computed their baseline information like body surface area, heart rate, systolic pressure, diastolic pressure. And this is the differentiated signal which I have already discussed. This is the first systolic first peak, and dicrotic notch the second peak, and then it goes to the baseline, and the next cycle will start here. So this represents one cardiac cycle. So the algorithm that we have used to measure any feedback. So the algorithm that we have employed in this study to find out the augmentation index known as AIX. So first we take the differentiated ICG signal, pass it through the Butterworth Lopez filter, and we detect the highest crest and call it as a B. And then we take this same ICG signal, pass it through second order differentiator, detect its highest crest and call it as A. Then we subtract A minus B here, and then we take the A again from the highest crest point and feed it to the divider. So you get A minus B by A, and that gives me the augmentation index AIX. So this AIX will tell us whether the group of patients belong to the normal category or to the other disease category. So this is the algorithm for calculation of blood pressure and the heart rate. So here again, what we did, we computed the impedance in the similar way, and afterwards we have taken this augmentation index, that is a minus b by a here. So then we feed this to the comparator. So whether augmentation index is equal to 1.7 or less than or equal to 1.7 or not. So if it is yes, that means the subject is healthy. We display the patient's systolic pressure, diastolic pressure, and the other heart rate and other parameters. If the augmentation index is not less than 1.7, that means if it is more, then we subject is we say that the subject has some abnormality related to coronary artery disease. Then we do the calculation of systolic, diastolic pressure, heart rate, and we display the parameters. So this is the overall structure of the algorithm. So we found a correlation between estimated parameter and the extracted features. So for the P1 minus P2, the first cardiac cycle, so systolic pressure, we have correlation of minus 0.21 minus 0.11 for diastolic. Heart rate is minus 0.08. Uh, so you can see that augmentation index has a correlation value of 0.99 for systolic, 0.95 for diastolic, and for heart rate it is 0.78. So for both systolic and diastolic pressure, we have a good correlation. For the heart rate, we still have much lower correlation compared to the systolic pressure. And we use this model to fit in this augmentation index. So what we have done is, so when we are measuring systolic pressure of the interventional group, it is 25 into this augmentation index plus 142. So this is our model that we proposed. Uh, so based on this, we have computed for comparison between the uh, interventional group and the control group. So interventional group is the one the subjects are with cardiovascular ailments, and the control is the one with the normal group of subjects. So likewise, we computed also for diastolic pressure with intervention and conventional control group and the heart rate. So the results what we analyze here is systolic pressure, diastolic pressure, and the heart rate. Uh, the this plot shows predicted and actual values of systolic pressure. You can see here. Uh, this is the augmentation index. Augmentation index is the parameter that we have identified from the impedance cardiography. So we are comparing this with systolic pressure of the interventional group and systolic pressure of the control group. So we can see that there is a uh, agreement with predicted and the actual values. So we have one or two outliers here. Otherwise, most of them are lying on the line. So there is a good agreement. Similarly, for augmentation index versus diastolic pressure in case of intervention and control group, and then heart rate, augmentation index versus heart rate. So for heart rate, we have found that 78.78. So that is the reason the heart rate we do not have much predict correlation with the predicted and the actual values. So there is a deviation of the predicted values from the actual values that we observed in case of the heart rate. The systolic pressure, diastolic pressure, and the heart rate. So these are the deviations that we have observed. That means uh, uh, I mean, the accuracy needs to be further improved, or the the correlation has to be. I mean, we need to improve the correlation. Coming to the box plot here, again, this shows the systolic pressure, diastolic pressure, and the heart rate correlation with uh, the cardiovascular, disease patients with uh, the uh, you know, actual to the predicted. So this red plot shows the predicted uh, systolic pressure, and this is the actual pressure. So if you can see in all the plots, the pressure, systolic diastolic pressure is correlating with the augmentation index, whereas heart rate is not much. It is correlation index is around 0.78. So this needs to be improved, but that is shown here in the box plot. And we also use this Bland-Altman analysis. So this is one of the best analysis. And even in this group, those of you who are working on biomedical signal analysis, and those who are working on developing AI techniques for uh, you know, biomedical signals, so you can think of using this Bland-Altman analysis. So this analysis shows the agreement between two modes. That is, in this case, the impedance cardiographic measurement and the measurement made by the conventional mercury sphygmomanometer for blood pressure. So, um, so what happens? This technique validates the model developed using the regression analysis, and also establishes the good agreement between two modes of measurement by constructing the statistical limits of agreement. And this is again calculated based on the standard deviation and the mean values that that we have computed between the differences that we computed between two measurements. So this is the Bland-Altman analysis for systolic pressure in the deceased and systolic pressure in the control. So you can see that so this is the predicted values and the actual values of pressure, systolic pressure in the control group. You can see. So within this agreement, so we have a 0 plus or minus 5 here. So all the measurements lie within this range. So that shows that there is a good agreement. So you can clearly identify the outliers of any measurement. That is the advantage of this Bland-Altman plots. So similarly, we did Bland-Altman plots for other parameters like the diastolic pressure, then heart rate. So we can see compared to the pressure and the heart rate, so there is a large variation in the deceased compared to the normal of the control case. So here is a table shows regression coefficients, the error, mean standard deviation, and coefficient of variation. We could see that in, in, in case of pressure, you have maximum 0.99, 99% regression values. So compared to the pressure, this heart rate is is having less regression coefficient. So similarly, the coefficient of variation is also more in case of heart rate. Uh, so in a nutshell, I would say that pressure is much correlating with the impedance cardiography compared to the heart rate. So maybe we need to figure out and see where uh, what information, we proposed, and we measured different hemodynamic uh, baselines. So these are the baseline parameters. Like after studying the recording the heart rate, the pressure, we also all these parameters are measured from the ultrasound or echocardiogram. So echocardiogram is a technique used to measure the amount of blood that is ejected out from the left ventricle of the heart for every cardiac cycle. And during this procedure, so there are different parameters like the left ventricular ejection fraction, stroke volume. Stroke volume is the amount of blood that is ejected out per minute from the left ventricle. Then left ventricular end systolic volume and diastolic volume, then isovolumetric contraction time, then isovolumetric relaxation time, and then total systolic time, total diastolic time, and lastly the performance index of the myocardium. So these measurements are done in the echocardiogram parameters, and we have used all these parameters. Of all this, stroke volume and left ventricular ejection time and ejection fraction, left ventricular ejection fraction. So these are the three important parameters, but the other parameters are also of clinical importance. So here is a sample diagram that shows how uh, echocardiogram were captured in a particular patients in different modes. Like this is a biplane mode, this is a four-chamber mode where you can clearly visualize all the four chambers, and also accordingly you would be able to measure what is the amount of blood that is ejected out from the left ventricle. And the lower diagram shows the pulse Doppler mode where you correlate the flow of blood in these chambers with reference to the time axis. So the time axis here is the electrocardiogram. So electrocardiogram will be taken as a reference, and with reference to electrocardiogram time, we will measure what is the amount of blood that is injected out. And these are the features that is used as a predictor. One is systolic time, diastolic time, ratio of systolic and diastolic time, the systolic and diastolic area, a difference of first two peaks expected in the cardiac cycle. As I told you, that is in the first cardiac cycle, P1 and P2. In the next cycle, P3, P4 differences also we have expected. And finally, augmentation index is the parameter that we measured from impedance coordinate. This is a schematic representation of the implemented artificial neural network. So we have taken the input neurons, and then we feed it to the network, and we have several hidden layers. Then we have a output layer. From the output layer, we estimate the echocardiogram parameters. So the model developed here is that output is given by mx2 plus c. So this is the equation, and these are the values of the m and c values that is developed from this model. So we propose this values of m and c for each output parameters of the echocardiogram, and then we arrived at the ANN optimization. So what we did is that we after using these m and n, m and c values, we optimize the uh, number of neurons that is required in the hidden layer, and finally uh, we we also did the optimization based on the training the ANN. So what we did is we selected three different methods. One is a Bayesian regularization, Lieberberg method, and a scared conjugate gradient. So these three algorithms we trained for the ANN for different number of epochs, and finally for all the hemodynamic parameters like stroke volume to all the parameters that is being considered here. So after training this, also we used the weight matrix for different neurons, and like these are the different parameters, and these are the number of neurons. And finally, we arrived at the final number of neurons after optimization for each parameter. So we were able to downsize the number of neurons, required number of neurons based on optimization. And we also evaluated the results for all these parameters, starting with stroke volume, with all the left ventricular parameters like end systolic and diastolic ejection fraction, and along with the time parameters. See, one is volume parameters, this is the time parameters. Here you can see the regression coefficients and error with 8 neurons. So after by using 8 neurons, we were able to get the regression values more than 80% in some of the key parameters, like stroke volume is 83, and systolic volume 89, diastolic volume 87, ejection fraction is 95. See, among all the parameters I told you, ejection fraction is one of the important parameter, and we have got much higher regression coefficient. At the same time, error is also important. We should try to minimize the errors. In some cases, we are having error goes up to 20%. So this is still not acceptable. So we have to see where we could test this. This is the mean value and the percentage error. So if you can see, the percentage error in this case goes up as much as 16%. Then regression coefficients and error obtained with reduced neurons. So in this case, in the other case, we used 8 neurons. So here we have used 6 neurons. We have considered 6 wherever it was proposed as per the model. We computed with the reduced neurons. We did not find any much difference here. For example, left ventricular ejection fraction has gone down to 90, whereas in case of 8 neurons it was 95. So likewise, like in the previous studies, here also we did Bland-Altman analysis, and for all the hemodynamic parameters like stroke volume, then end ventricular systolic volume, and diastolic volume. So for all we did it, and you can see the outliers are very minimum. So we do not have much outlier. I mean, it is agreeing with the two, the augmentation index and the hemodynamic parameters. So similarly, you could, I mean, in most of the Bland-Altman plots, you can see that outliers are minimum. Then after this Bland-Altman, yeah. So this is our standard deviation and coefficient of variation of the difference between actual and the predicted. So here again we could see the coefficient of variation for all the hemodynamic parameters. We could see that in some of the contraction time and the time parameters, relaxation time and the ejection time, so the standard deviation is much larger. So When it comes to left ventricular ejection fraction, it is 3.4. It is much acceptable here. And overall, myocardial performance index is up to 10%. It is much accepted, as well as standard deviation is much lower. Now, after this, the second one is, we have a time, or Dr. Holly? Okay, let's continue. In the second experiment, we did detection and localization of coronary arterial stenosis. In this case, what we have attempted to do is, we have taken the baseline characteristics of the same group. In this case, number of patients studied were 50. Again, this is an interventional group, because everybody in this group went through the angiogram. Angiogram is an invasive procedure. It is performed with certain assurance of the stenosis in the artery. So these are the three main arteries. One is left main coronary artery, left anterior descending artery, diagonal branch, left circumflex artery, and the right coronary artery. So these are all the main branches in the coronary artery system, and we try to correlate augmentation index with all the uh, branches and see whether we would be able to do that. So as you know, this is a sample angiogram that is recorded from the patient. So you can see that there is a blockage here, and this is identified by the invasive procedure. And again, there is one more block that is observed here. So we need to correlate these blockage in a specific branch with the impedance cardiography, and try to bring in correlation with impedance augmentation index to the uh, you know the location of these blocks and identification of those arteries. So again, we try to use the artificial neural network here, and this is the proposed model that we did, and the stenosis were studied in these branches, that is LNCA, then LAD, left anterior descending artery, then diagonal branch LCX and RCA. So these are all the three major coronary artery which are important for supply of oxygenated blood to the heart itself. And we also map the confusion matrix. So this is the actual values that we predicted, and this is the actual values measured, and this is the predicted value. So we can see that for diagonal branch, we have we were able to predict uh, no blockage in the actual and no blockage in the predicted. So diagonal, we were able to predict better. When it comes to the LAD, so we were not able to do that, because in the predicted there was a zero blockage in the no block, but in case of actually we found 9. So similarly, in case of LCX branch, so we were able to identify no block in the predicted around 12, but in the actual there was 0. So there was no match in the fusion matrix. So similarly, in case of predicted no blockage, we found 8, but in the actual no blockage, it was more. So again, we did not, got any conclusive, outcome. So in the case of the another branch RCA, the no blockage we found 2, whereas no blockage in the actual it was 14. So again, so if we compare the whole, com- uh, 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 the blockage in the coronary arteries with the augmentation index, so we can see that the prevalence is much lower. So the prevalence is much lower. So only in case of LAD and LAX we have 78 to 76 prevalence, but the others are lower. Similarly, when it comes to the accuracy, diagonal is more, diagonal is highest, followed by LAD 80, and the rest is 70s, and RCA is also 80. So this, much percentage of accuracy is still not enough. So we could only able to, predict for diagonal branch. Then we have a precision and sensitivity. So again, for diagonal it is 71% sensitivity. Whereas for the LAD it is 100. And then again specificity, if you look at it, 100 is a specificity for the LCX. So if you take a overall F score, LAD is having 89 and diagonal is 71 and LCX is 82. So in summary, I would say that the study what we did is only for total number of patients 50. So by considering the total sample size, uh, uh, you know, uh, this is much too early for us to predict. So maybe we should increase the sample size. So in conclusion, uh, I propose generalized 2D electroskin model. It's a non-invasive, cost-effective for cardiac health monitoring for mass screening application. Proposed for detecting cardiac abnormalities, and this is also a method of cuffless estimation of blood pressure and heart rate. So you don't need to place a cuff on the arm and measure the pressure. So you can measure the blood pressure without using the cuff. And hemodynamic parameters can be extracted without the supervision. And the last conclusion is that detection and localization of coronary artery stenosis. Again, this study is only preliminary. I mean, this has to be done, by increasing more sample size and bring in good correlation. So until then, I would say that this is, it's an ongoing research work. Yes, yeah. So after this, I mean, we came up with one patent of this proposed device, and also this work was published in Artificial Neural Networks. So, and then I would like to acknowledge our clinical collaborator, with whom we are able to record signals from all the cardiac patients in the ICU. Um, we were able to access the ICU and record signals from all the patients. And also we thank the patients who participated in this study. So I thank you all for your kind attention, and any questions I would be happy to take it.
Hello.
Yes.
Yeah, Banjana sir, thank you very much. Myself, Dr. Santosh Kumar,
Yeah.
course co-coordinator from University College of Engineering.
Okay.
Thank you very much, sir, for your valuable information for the research.
Yeah.
I have asked the participants to post the questions in the chat. So waiting for it, sir. Any of the participants would like to communicate with the resource person, please feel free enough to communicate now.
So I am seeing here there was no such question as being given in the chat.
Yes, sir. Yes, sir. We'll wait for 2 minutes, sir.
Yeah, yeah, sure.
Any queries from the participants? You can speak with the resource person.
इधर हाँ मंजन इधर dear participants, anybody has any questions to the speaker?
Yeah, there is one Golanpalli V. Prasad. He has a question, but he did not type it.
Yeah, sir, question is related to just his type, but question is not typed. Yeah. Participants, you can unmute and speak with sir directly. Because we have another 5 minutes to wind up this session. Anybody can unmute and directly speak with sir so that any clarification you want, you can able to clarify.
Sir,
Yes, yes.
what are all the different quantization method we can use, sir?
For data analysis?
Yes, sir.
No, quantization in the context of what? What data
Actually,
you are?
In the machine learning,
Okay.
suppose any classification data set is there.
Okay.
What kind of the quantization method can be used, sir?
I mean, it depends on the data size. So there are many statistical models available. Based on the data, we may use appropriate quantization techniques. So if you can give me the relevance of the data and the sample size, I can tell you. But there are many statistical tools available for quantization.
Okay, sir.
Yeah.
Any other participants? Any more questions? You can unmute and speak with sir. So,
Yeah.
If there are no questions from the participants, on behalf of Institute and on behalf of organizing committee, and personally I thank Dr. Manjunath sir for sparing his valuable time and discussing his research findings and the technological advancement which are happening in the field of the biomedical engineering, particularly in the hemodynamics and the application of machine learning or ANN to the important research area. Okay. Sir, on behalf of participants also, I thank you, sir, for sparing your valuable time.
Thank you.
Thank you. So
Yeah.
participants, we are going to meet again at 3 o'clock. All of you log in by 2:45. So that is for the final session. Before I conclude this session, there are some inputs I wanted to give as a coordinator. Beyond the session attendance, what we are taking, we'll be also taking the attendance during the sessions. Okay, not only from the Google form. So all of you see that you will attend the last session without missing, because that will be 3 to 4 we will have presentation from Dr. Suryakant Vigan Shetty. He will be discussing for about 1 hour of AI and ML applications in biomedical field. Followed by from 4 to 4:30 we will have interaction and the feedback session. That feedback session where some of you get prepared to speak about the FDP and how it has went on and what is your experience for 5 days. And also at this moment I wanted to give information that you need to do certain the formalities. Okay, so you need to complete some formalities in the Atal FDP the portal also. There will be some feedbacks may be there for you, and some processing you need to do by login through your ID in the Atal FDP portal. Okay, I suggest you after completion of the this final session, and also after giving your session attendance, second session attendance and third session attendance, and completing the feedback, and after completion of the test, I suggest you to log in into the Atal FDP portal and complete the formalities in the Atal FDP also. Okay, and with reference to the test, as already my fellow colleagues have already told, that test will be simple. It will not be to worry much. So that will proceed you after the final session is gets over. Okay. If anybody,
sir, could you please repeat it, sir?
Madam, that is only after the third session. Okay. So, we have already anyway posting the Google form for the session attendance. Okay.
Okay.
After that, we will be posting the feedback form and the test form also. Okay. All of you complete that feedback form in the test form. Then,
okay, sir.
Doing that, there will be some formalities you need to complete in the Atal FDP web portal also by logging in your ID.
Okay, sir.
You can complete that also, because unless you complete those formalities, your certificate will not be generated. Okay.
Should we do the feedback there also in Atal portal, sir?
I don't know, because the student version will be different. Okay, the participant version of the web page will be different. That's why what I suggest, you can log in into the and find out what formalities you need to complete there.
Okay, okay, sir. Okay.
So if anybody has any other queries, I can answer you.
So in the afternoon session, what is the plan? What is the session, sir? Afternoon?
That is only from 3 to 4. The Professor Suryakant Vigan Shetty will be delivering for 1 hour.
Okay, okay.
Followed by 4 to 4:30, we will have an interaction and feedback session.
Okay, sir.
Oral feedback means through your microphone.
After that only test is there. After that test.
4:30, once we wind up this official session, we post on the WhatsApp group the test question paper, that is the Google form test question paper, as well as the feedback forms. Okay.
Okay. It will be active till what time, sir?
Probably by 7 p.m. also it will be active. Yeah.
Okay, okay, sir. Thank you, sir. Thank you.
So,
okay,
is there any queries from the participants?
But materials have not been given. Will the questions in the test will be easy or what, sir? Because all the PPTs you have not shared.
If you have a minimum this one information about the artificial intelligence and the machine learning, and 2 things about the biomedical engineering, I don't think
Okay.
it's very difficult for you to attend. Because we have not taken any question directly from the presentations of the speakers. Yes.
Okay, sir. Okay, sir.
We are also posting the PPTs of most of the speakers through your WhatsApp group. Yeah.
Okay, sir. Thank you, sir.
Okay. So thank you, sir. Manjunath sir, thank you once again.
Yeah, thank you. So I have one of the journal paper. If you want, you can share it with them. So
Okay.
I can
You
share.
just send it, sir. You send it to my email. I'll
Yeah.
share with you. Yeah.
You can share it with them, so they
Okay.
can use these techniques.
Yeah, definitely, sir. Yeah, thank you.
Okay.
Okay. So we are breaking for lunch now. I request all the participants to rejoin by 2:45 and sharp at 3 p.m. we start the third session. Right?